Here in this session I am going to explain about the two-port networks. Two-port network. So it comes under unit number 4. So two-port network. Here any network can be represented with a rectangular box. So let us consider a network which was represented with a rectangular box. So this is a network. If the network consists the two terminals, like this, then these two terminals together called as a port. Port means two terminals together called as a port. If the network consists only two terminals or only one port, then that network is said to be one port network. If the network consists four terminals or two ports, so it is one port and it is another port, then that network is said to be two port network. So it is said to be a two port network. And this two port network have four variables here. Those variables are voltage V1 and current I1. Here this is the voltage V2 and this is the current, which these currents are represented into the network, and the terminals is named as 1 dash. These terminals are named as 2 dash. The port at which the excitation is given, that is known as input port, and the port where the load is connected is known as output port. Among these four variables, any two variables can be represented in terms of other two variables. That means, suppose for example, these two variables V1 and V2 can be represented in terms of I1 and I2. That means these may be represented as a function of I1 and I2. Like that, V1 and I1 can be represented in terms of V2 and I2. That means these V1 and I1 are the function of this V2 and I2 here. So here among these four variables, two variables can be represented with another two variables. That means the total number of combinations will be 4C2. Among four variables, these two variables can be represented with another two variables. So these 4C2 combinations will give, this is 4 factorial divided by 4 minus 2 factorial into 2 factorial. So that is 4 into 3 into 2 into 1 divided by 2 factorial means 2 into 1 into 2 factorial means 2 into 1. This 2, this 2, this 1 will get cancelled. So the total number of possible combinations will be 6. That means what I want to say here is there will be 6 combinations like this will be present. So depending upon the combinations, these parameters are classified. First one, the parameters. Here the parameter, here the parameters. Let us consider these parameters. And the variables. And the equations are a representation of these variables. First, let me consider, first one is here open circuit parameters. So in this open circuit parameters, these variables expressed variables in terms of, so these expressed variables here are in this open circuit parameters, this V1 comma V2 can be expressed in terms of I1 and I2, and these equations so represent how to express these variables in terms of these currents, that is the matrix notation, matrix representation, and the equation. So let me write for one parameters so that you can understand what is this. So in this V1 and V2 can be expressed in a vector matrix form like this: V1 V2, that is equal to, it is Z11 Z12 Z21 Z22, and this is I1 and I2. So it is that means these variables, this V1 and V2 variables can be expressed in terms of I1 and I2 with the help of these parameters. These parameters are said to be open circuit parameters, or Z parameters, or impedance parameters. So the names, the different names for these open circuit parameters are open circuit parameters, or impedance parameters, or Z parameters. And in equation representation, these can be represented like this. So here V1 is equal to, so this V1 is equal to Z11 I1 plus Z12 I2. So this equation represents V2 is equal to Z21 I1 plus Z22 I2. So similarly, another parameters will also be there here. Another parameters here are second one, short circuit parameters. Short circuit parameters. In this short circuit parameters, the parameters I1 and I2 can be expressed in terms of V1 and V2. So how to write this? You can see I1 is equal to, I1 I2 is equal to, it is in vector matrix form. It is Y11 Y12 Y21 Y22. It is V1 V2. And in equation representation, these things I can represent it as I1 is equal to Y11 V1 plus Y11 V1 plus Y12 V2. Here I2 is equal to Y21 V1 plus Y22 V2. So just if I bring this I1 and I2 to the left side of that equation and bring this V1 and V2 to the right side of this equation, then these parameters can be obtained. Just I am replacing these matrices here. So these are the admittance parameters, or short circuit parameters, or Y parameters. So the another names for this open circuit parameter, another name here are, it is Z parameters, or impedance parameters, Here also the short circuit parameters can also be called as, it is Y parameters, another name Y parameters, or admittance parameters, admittance parameters. Next thing here, another parameters here are, third one is transmission parameters, or another name for these are ABCD parameters, or chain parameters. They are also said to be chain parameters. Okay. So in these transmission parameters, these V1 and I1, these variables V1 and I1 variables can be represented in terms of V2 and minus I2. So here this V1 and I1 can be represented in terms of V2 and minus I2 here. So if I write it in a vector matrix form, I can write it as V1, it is I1, that is equal to, it is A, B, C, D into, it is V2 and minus I2. Okay. So the negative side for this I2, the reason behind the negative sign for this I2 is actually in transmission parameters, if the power sends from this this terminal to this terminal, this is source and it is load, it is a transmission line. For example, in case of transmission parameters, the power or the current will flow like this. That means the current will be the actual current direction of this current will be opposite to that of this current. So I am representing this I2 with minus I2 here, right? So if I write this vector matrix form into equation notation, V1 is equal to is AV2 minus BI2. This I1 is equal to CV2 minus DI2. So it is a equation representation of these parameters. Next, fourth one is inverse transmission parameters. Inverse transmission parameters are A dash, B dash, C dash, D dash parameters. So in this, just these V2 and I2, these variables V2 and I2 can be represented with V1 and minus I1. So in vector matrix notation, I can write just this V2, this replace this matrix with this matrix and this matrix with this matrix. So V2 and I2 is equal to this A dash, B dash, C dash, D dash, and it is V1 and minus I1. So if I write it in a equation notation, this will become V2 is equal to A dash V1 minus B dash I1. So this I1. Next, I2 is equal to C dash V1 minus D dash I1. So this is how we can express this V2 and I2 in terms of V1 and I1. Next parameters here are hybrid parameters. Hybrid parameters or H parameters. So in these H parameters are hybrid parameters. This V1 and I2 can be represented or can be expressed in terms of I1 and V2. So V1 and I2 can be expressed in terms of I1 and V2. So how to write in a vector matrix notation here is V1 I2 is equal to, it is H parameters H11, H12, H21, H22, and this is I1 and V2, it is I1 and V2. So I can represent in equation notation here is V1 is equal to H11 I1 plus H12 V2, and this I2 is equal to H21 I1 plus H22 V2. So this is how these variables, among these four variables, two variables can be represented with the another two variables in terms of Z parameters, Y parameters, or ABCD and hybrid parameters. Next, sixth parameters here are inverse hybrid parameters. So these are inverse hybrid parameters or G parameters. So in this just this I1 and V2 can be expressed, I1 and V2 can be expressed in terms of V1 and I2. So let me write this vector matrix notation here. I1 it is V2, that is equal to, it is G11, G12, G21, G22. This is V1 and I2. So in a equation notation, this I1 is equal to G11 V1 plus G12 I2. Next, V2 is equal to G21 V1 plus G22 I2. So this is I2. Okay. Next, let me explain all the parameters one by one here. So first, open circuit parameters are impedance parameters. So here first one is open circuit parameters. Open circuit parameters or impedance parameters. Or Z parameters. So in these parameters, let me explain one by one here. Here in this open circuit parameters or impedance parameters, the variables V1 comma V2 for a two-port network. This is a two-port network. The variables, these are the variables V1, I1, this is V2, this current I2. This V1 and V2 can be expressed in terms of I1 and I2 in case of these open circuit parameters. That means this V1 and V2 are the functions of this I1 and I2. So I can represent it in a vector matrix notation as V1 V2 is equal to Z11, it is Z11, Z12, Z21, Z22, it is I1, I2. That means these variables can be expressed in terms of this I1 and I2 using these impedance parameters. So these are the independent parameters, these are the dependent parameters on these parameters. These are the independent parameters and these are the dependent parameters. So this V1 I can write it in equation notation representation, V1 is equal to Z11 I1 plus Z12 I2, and this V2 is equal to Z21 I1 I1 plus Z22 I2. So from this Z11 can be calculated like this. So these Z11, Z12, Z21, Z22, these are called as Z parameters, open circuit parameters, or impedance parameters. How to find these parameters? So first one, by opening, that means open circuit port 2. So it is port 1 dash, it is port 1, and this is port 2. If I open circuit this port 2, this I2 will become 0 here, because in open circuit there will not be any current flow will happen. So here open circuit port 2 means I2 is equal to 0. If I make I2 is equal to 0 in these equations, this V1 is equal to, that means if I2 is equal to 0, V1 is equal to Z11 I1. So next V2 is equal to Z21 I1. So from this Z11 is equal to V1 by I1 by making I2 is equal to 0, and Z21 is equal to V2 by I1 by making I2 is equal to 0. So this Z11, Z21 can be calculated like this, and this Z11 is called as driving point, because it is Z11 driving point input. So it is this is calculated at input, so it is the driving point input impedance Z11 driving point input impedance with port 2 open circuited. Next, this Z21 or this Z11 can also be called as open circuit. Simply it is open circuit input impedance. This Z21 can be called as, it is transfer impedance with port 2 open circuited, or it is also known as open circuit forward transfer impedance. Open circuit forward, since it is V2 by I1, it is forward. If it is V1 by I2, that is reverse transfer function. So it is open circuit forward transfer impedance. Next, that means by opening port 2, I am able to calculate this Z11 and Z21 parameters. Next, second one is open circuit port 1. If I open circuit port 1, what happens here? That means if I1 is equal to 0, if I make I1 is equal to 0 in these equations, V1 is equal to Z12 into I2, V2 is equal to Z22 into I2. So let me write these equations here. V1 is equal to Z12 I2 and V2 is equal to Z22 I2. So from this Z12 can be calculated V1 by I2 by making this I1 is equal to 0, and Z22 is equal to V2 by I2 by making I1 is equal to 0. So this Z12, Z22, these are the impedance parameters, and this Z12 can be called as, it is V1 by I2, so it is called as transfer impedance with port 1 open circuited, or this is also called as open circuit reverse transfer impedance. Next, Z22, this is called as driving point output impedance, with port 1 open circuited, or it is also named as open circuit output impedance. So these are the names of this Z11, Z21, Z12 and Z22. So this is how we can calculate these values of Z11, Z21, Z12 and Z22 for any network. Next, condition for reciprocity and condition for symmetricity. So if you want to say any network is reciprocal, there are some conditions to be followed. So in terms of Z parameters, so what is the condition for reciprocal network and what is the condition for a symmetrical network, I am going to derive here. So condition for reciprocity, first one, condition. So in terms of, it is in terms of Z parameters, condition for reciprocity. So the network is said to be reciprocal. Here this network is said to be reciprocal if the excitation at one port, what is the condition for reciprocity here is, the network is said to be reciprocal if the ratio of response at one port to the excitation at the other port is same even when the response and excitation are interchanged. So let me explain it clearly. Suppose here it is a two-port network. For this two-port network, I am giving the excitation here. So that excitation is V1, let us assume, and this is the terminals here, and this is the current I1, this is the current I2. Actually this is V2, the voltage across this one is V2. While we are calculating the condition for reciprocity, one of the ports should be shorted. So now I am calculating the response here. Let us take, it is I2 dash. This current is I2 and this current is I2 dash. Here if I apply the excitation at this port 1, it is port 1, it is port 2. That means this excitation is, let us assume it is V1 is equal to Vs. Now here the conditions here are V1 is equal to Vs and I2 is equal to minus I2 dash, because these two are in reversal. If this current is flowing like this current is flowing in this opposite direction. So it is I2 is equal to minus I2 dash, and this is short circuited, means the voltage at this port 2 is 0, V2 is equal to 0. Now what I mean to say here is, from this reciprocity definition, the ratio of excitation to the response or response to the excitation is same even when the response and excitation are interchanged here. That means the ratio of excitation at one port, that is Vs, divided by response at the other port, that is I2 dash, should be same even when the excitation and response are interchanged. So it is for figure 1. Next thing here is, I need to calculate this ratio by interchanging this excitation and response here. Now I am taking the excitation, now I am taking the response here, I am applying the excitation here. So now it is V1, that is equal to Vs source, so that it is V2 is equal to Vs, so it is I2. Now this is I1, and whenever I am applying the supply, this current will flow like this, so it is I1 dash. So it is a two-port network. So here the ratio of excitation to the response, here this Vs is excitation after interchanging the excitation and response. Now this V2 is equal to Vs is the excitation, and response here is I1 dash. Now it is Vs by I1 dash is the ratio of excitation at one port to the response at the other port. These two should be same for the reciprocal networks. That means the condition for reciprocity can be obtained by equating this Vs by I2 dash is equal to Vs by I1 dash. So I need to find this Vs by I2 dash by using these conditions. So what is this equations here? Let me write these equations here. V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. Now substitute these things here. V1 is equal to Vs, so V1 is equal to Vs, and I2 is equal to minus I2 dash, so Z11 into I1 minus Z12 into I2 is equal to I2 dash. I2 is equal to minus I2 dash. If I substitute, I will get this one. Next, V2 is equal to 0 here. 0 is equal to Z21 into I1. It is in place of I2, if I replace with minus I2 dash, it will become Z22 I2 dash. Now what I need to find here is Vs by I2 dash. So Vs by I2 dash. So if I want to find this Vs by I2 dash, I need to find this I1 in terms of I2 dash, so which can be obtained from this equation. So Z21 I1 is equal to Z22 I2 dash. Now I1 is equal to Z22 divided by Z21 into I2 dash. So now substitute this I1 equation in this expression. So Vs is equal to Z11 into, in place of I1 replace with this one, Z22 divided by Z21 into I2 dash minus Z12 into I2 dash. Same thing. So now rewrite this one. So it is by taking I2 dash as a common, take I2 dash common here. So it is Z11 Z22 minus Z12 into Z21 divided by Z21. So it is Vs. Now you find this Vs by I2 dash. Vs by I2 dash is equal to, it is Z11 Z22 minus Z12 Z21 divided by Z21. So let us consider this one as equation number 1. Now we should find this Vs by I1 dash. Now in this what are the conditions here? This V1 is equal to, it is a short circuited, so V1 should be equal to 0, and I1 dash is equal to, or I1 is equal to minus I1 dash. I1 is equal to minus I1 dash, and this V2 is equal to Vs here. V2 is equal to Vs. Let us substitute these values in these equations. Now V1 is equal to 0. So now V1, so in these expressions, what are these expressions? V1 is equal to Z11 I1 plus Z12 into I2. V2 is equal to Z21 I1 plus Z22 I2. If I substitute this V1 is equal to 0 in this one, 0 is equal to I1 is equal to minus I1 dash here. So it is minus Z11 I1 dash plus Z12 into I2. Next, if I substitute the same thing, V2 is equal to Vs here. So Vs is equal to, in place of I1, replace with I1 minus I1 dash, Z21 into I1 dash plus Z22 into I2. Now if I want to find this Vs by I1 dash, I need to write this I2 in terms of I1 dash. So from this I can write this I2 is equal to, from this Z12 I2 is equal to Z11 I1 dash. So I2 is equal to Z11 divided by Z12 into I1 dash. Now replace this I2 with this one. I will get Vs is equal to minus Z21 into I1 dash plus Z22 into I2. In place of I2, Z11 divided by Z12 into I1 dash. Now take this I1 dash as a common here. If I take this I1 dash common, it is Z11 Z22 minus Z12 into Z21. If I multiply with this one, I will get this one divided by Z12. So that is equal to Vs. Now what I need to find this Vs by I1 dash. So Vs by I1 dash is equal to Z11 Z22 minus Z12 into Z21 divided by Z12. So let us make this equation as 2. So according to the definition of reciprocity, or if you want to say the two networks are reciprocal networks, then the ratio of excitation at one port to the response at the other port is same even when the excitation and response are interchanged. So the meaning of that reciprocity theorem here is these equations should be same. That means Vs by, so from reciprocity condition, from reciprocity theorem or reciprocity theorem, this Vs by I1 dash should be equal to Vs by I2 dash is equal to Vs by I1 dash. That is equation number 1 should be equal to equation number 2. So what is this Vs by I2 dash? From this Z11 Z22 minus Z12 into Z21 divided by this Z21. This Vs by I1 dash from this equation 2, that is Z11 Z22 minus Z12 into Z21 divided by Z12. So this one and this one will get cancelled here. So finally Z12 is equal to Z21. So this is the condition for the networks to be reciprocal in terms of Z parameters. So Z12 is equal to Z21 is the condition for reciprocal networks. Next, the condition for symmetricity in terms of Z parameters. Condition condition for symmetricity. Okay. The network is said to be symmetrical. Two-port network. Let me consider a two-port network here. So this is V1, 1 dash input port, I1. It is V2, it is I2, 2 dash. So the network is said to be symmetrical if the ratio of voltage to the current at the same port should be equal. Should be equal to the ratio of voltage to the current at the other port. That means this V1 by I1 should be equal to this V2 by I2. That is what I am saying here. So the ratio of voltage to the current at one port should be equal to the ratio of voltage to the current at the other port with other port open circuited. Let me explain that. So first one, I am finding here V1 by I1. V1 by I1. The ratio of voltage to the current at one port, V1 by I1, by making other port open circuited. That means I2 should be equal to 0. So this is the condition here. That means if I draw this one, the same two-port network will be like this. So this is let us consider it as V1 and it is I1, same network. It is a two-port network, and this is 2 dash, 1 dash. It is I2, it is V2. So this second port should be open circuited while I am calculating the ratio of voltage to the current at this port. So V2 is equal to 0. So if I substitute this I2 is equal to 0, now I am giving the here the excitation V1 is equal to Vs. Let us consider here V1 is equal to Vs. So the conditions here are V1 is equal to Vs and I2 is equal to 0. So these are the condition while I am calculating this V1 by Vs or Vs by I1. So Vs by I1 calculate here because V1 and Vs are both are same here. So now what is the equation for these impedance parameters? V1 is equal to Z11 I1 plus Z12 I2 and V2 is equal to Z21 I1 plus Z22 I2. So if I substitute this in place of V1 with Vs and I2 is equal to 0, Z11 into I1. Now it is Vs by I1. The value of Vs by I1 here is Z11. Let us consider this is equation number 1 and try to find this, try to make another network here. Now the excitation here is V2 is equal to Vs. Here I am applying the excitation here and this is I2. It is the same two-port network. Here this is this I1 should be 0. Another port should be open circuited. I1 is equal to 0. So the condition here is V2 is equal to Vs and I1 is equal to 0. Now I need to find this Vs by I2. So I have to find this Vs by I2. So use the same expressions here. V1 is equal to Z11 I1 plus Z12 I2. V2 is equal to Z21 I1 plus Z22 I2. So if I substitute this I1 is equal to 0 and V2 is equal to Vs, this expression will become Vs is equal to Z22 into I2. Now what I need to find here, Vs by I2. So Vs by I2 from this is equal to Z22. Let us represent this equation as 2. So as per the definition of symmetricity, these if I want to say the two networks are symmetrical networks, the ratio of voltage to the current at one port should be equal to the ratio of voltage to the current at the other port, by making the other port open circuited. Right. So now that means this equation number 1 equal to equation number 2 as per the definition of this symmetricity. So Vs by I1 should be equal to Vs by I2. So what is this Vs by I1? Z11 is equal to Z22. So this is the condition. This is the condition for the network to be symmetrical in terms of Z parameters. Next thing here is representation of the two-port networks with its equivalent network in terms of Z parameters. That means equivalent circuit of the two-port network in terms of Z parameters. So now you see what are the equations here is V1 is equal to the Z parameters equations here are V1 is equal to Z11 I1 plus Z12 I2, and another equation here is V2 is equal to Z21 I1 plus Z22 I2. Let us represent this is equation number 1 and it is equation number 2. So what is this? This is the equivalent circuit of, let me explain this concept here, equivalent circuit representation of two-port network in terms of Z parameters. So here this V1 is equal to Z11 I1. So this is the two-port network. You know that it is two-port network. This is V1, this is I1, V2, this is I2. So this two-port network equivalent circuit representation in terms of Z parameters I am going to find here. So this is V1 I1, this is okay. So from this equation, if I write this like this, it is Z11 and it is plus and minus, it is Z12 into I2. So it is plus and minus, it is V1. So if I apply the KVL for this equation, for this loop here, V1 is equal to this voltage is equal to this voltage plus this voltage. So this voltage V1 is equal to this voltage is the current into the impedance Z11 into I1 plus this voltage Z12 into I2. That means this equation number 1 will satisfy this network. Next, coming to the second port, here this is I2, it is I2, and this is V2, it is V2, this is I2. So now I can represent this network as like this. It is here it is plus and minus. Now it is I2, it is Z22 into I2 plus Z21 into I1. So if I combine these two networks, so now this is the equivalent circuit representation of a two-port network in terms of Z parameters. So this is the two-port network equivalent circuit representation in terms of Z parameters.